Now I'll let Radu talk about those time-based indices I've mentioned.
Yeah, but before I go to that, I saw some hands going up at one point, and maybe you have some questions, so I think we can take a bit of time to, just in case we went, go on.
So just to understand kind of the overall architecture here, when you're talking about nodes, you're talking about separate physical hosts or separate data stores.
Well, you can. What Rafal just did was it started multiple nodes on the same machine, right, which is this laptop. But normally you would have separate servers. I mean, only in, say, extreme situations you would have multiple nodes on the same server. For example, we have huge servers. But yeah, usually we're talking about different servers. Yeah.
Different data stores as well.
Sorry?
There's also different data stores?
No, you can spread the one index onto multiple servers. That's the whole point of shard.
Usually, yes, you have the data on the local storage for that particular node. So if the node itself actually holds it in the local storage on the local disks, so it's not in shared file system or anything like that. Local file system, and each node uses that. That's why there's a notion of replicas, so you can replicate the data, have more than one physical copy of the documents that you've indexed.
Well, you can always use like network storage and mount that to a local file system, but that usually doesn't perform well because Elasticsearch kind of needs fast response times from the I/O. And then, we tried this because, we want cheap storage, of course, and we always bumped into this problem that kind of network storage is kind of a no-no. Like if you want Amazon EBS and things like that, they probably only work for like niche use cases.
Yes.
Since it's a cluster, is it managed behind a bit? Is that Elasticsearch manage that for you, or is that something that's managed by some other service?
Okay, no, it actually Elasticsearch does that on its own. The point is, you start the first node, and it says, okay, I'm alone, so I'm going to be the master of this cluster of me. Okay. Well, you hit a node. If you want to take this, go on.
Yeah. So that depends on the request actually, because there are parts of the request. In general, Elasticsearch cluster is divided into numerous roles. Each node has. You have the master node, which is actually the one that handles the cluster state and all the operations that requires the cluster state to change, like joining a node, kicking out a node, or changing the mappings and stuff like that. Searches go round robin through all the nodes. So Elasticsearch will evenly try to distribute the searches across all the shards that are there, both primaries and replicas. You can have pure only data nodes that only have data and only return portion results, and you can have so-called client nodes that only don't have data, they are not masters, and are only used for running queries and aggregating the data from multiple shards, because that also requires some amount of work, like calculating the aggregations and merging that results together and returning the data to the client, requesting. So, but this is still everything that is done on Elasticsearch itself, and we can say invisible to the client that runs the query, or the request, or the settings change, or anything like that. This is all done. We have only an API that provides us with the possibilities, but we don't know what actually happens in Elasticsearch when we run the API. And it's a good and a bad situation. Good that in most cases, most user doesn't have to care about that, right? But it can lead to explosion of heap, for example, if you don't use it carefully. Any more questions for now?
Okay.
Follow up on that. Do you by chance have like a kind of a visual representation of this environment?
We don't.
Drawing of how you've architected this?
Oh, we don't.
In the trainings material.
Yeah,
but that's something.
No. I think there's in this book that you can grab. Definitely visual representations here. So if you didn't get one, you can get it now or later on or whenever you want. You're welcome. Okay.
It is. I don't remember.
So basically, I'm just going to draw them by hand, right? You have nodes, and then there are shards going into nodes, okay? And as one goes up, one goes down, shards migrate from nodes. That's kind of the visual.
Shards.
Yeah, right, shards and nodes. Okay. Any more questions? No. Okay, then I'll move on to some more scaling, which is kind of particular to the logs use case. And that would be using time-based indices. Let me just start from scratch.
Delete.
Sure.
I know we've done this with Elasticsearch and with Solar also. It's not just about CPU performance. We split up shards based off of memory consumption. So I don't know if you do that when you're architecting setups. If you think about how much of what's the size of the index, how much can I load into memory and do work, and that's how you decide how many shards you want.
That depends
Go on.
That depends actually on the use case, because the memory usage is different from use case to use case, right? So when you are using a lot of queries, the memory usage will be higher, especially with the aggregations or faceting in Solar. If you run, for example, an e-commerce site and you want to index your products, then you're expecting a lot of query requests. Usually in terms of logging use cases, the amount of query throughput is not that large, but still, memory is a valid concern. So yes,
the queries can get very expensive.
We can take into consideration when we are architecturing such stuff, the things like CPU, which is also a boundary for some, especially when the indexing is large. Because the analysis stuff takes time and CPU cycles. We need the memory because we need the memory to float either the field data for Elasticsearch or the doc values. A slight amount of memory, but still, especially for the clients node that aggregate the data, they need memory to aggregate all that stuff, especially with more and more queries coming in. And of course, the disks are also the bottlenecks, especially when you index a lot of data. This is where usually solid state drives are needed, and we are, for example, in a point where with some solutions that we need SSDs because magnetic disks are not performant enough to handle the load, and we keep growing with the queue of documents. So we need to index fast, and also we need CPU in that case as well. While the memory is not that of concern on that nodes that index the data, actually, but still it's something to consider when choosing, for example, the bare metal servers or EC2 instances or whatever you use for your environment.
So basically, indexing is CPU intensive, sorry. And when you search, you kind of use a lot of memory because you kind of has to keep all the data. So in my mind, it's like you need enough memory and enough disk space and enough disk I/O to sort of. That's if you don't have that, then your cluster will just be kind of unresponsive if you don't have enough for your data set and your needs. CPU is just a matter of how fast it goes. Okay, so obviously the more you have, the quicker your queries and things like that, but it's not the must resource.
I have
usually
experience in either of you guys with Elk, but what we've done with Elk, we've also split up indices based on we'll archive certain events or archive a set of events that happened a certain time ago.
I will cover that in just a second.
Well, perfect question.
A few more seconds, but yeah.
A perfect question for what Radu actually will show now.
Yeah. All right. So first of all, I want to talk about time-based indices because so that means just slicing your data up into indices based on time. For example, you want to keep your logs for 7 days, you can have 1 index per day because it's super easy in Elasticsearch to search through multiple indices. It will search in more shards. It's just the same thing. And why is that good? Because if you have, it's because of the way Elasticsearch indexes and deletes data. When you add a bunch of documents, they will make up a so-called segment, which is like a small inverted index within your shard. And that segment is immutable. Now that is good because when you're indexing, you won't invalidate the whole thing and have to rebuild the whole index. But it's bad because you can have loads and loads of those segments. So what happens in the background is that Elasticsearch will merge smaller segments into bigger ones. So if you have one big index and you keep pushing data to it, then you could have potentially very expensive merges. If you have time-based indices, let's say once per day, and you have 7 of them for 7 days of retention, then you're always indexing into that last index, which is much smaller than the overall thing. So the amount of merging that you're doing while indexing will be a lot smaller. So indexing will get a lot cheaper. Then when you're searching, you're typically searching only in recent data and maybe just every once in a while go back. And so if you have your data sliced up like this, then you can just decide where you want to search, and your searches will be faster, at least most of them. Of course, you can search in everything, and then that will be a tiny bit slower than having just one big index. But for most use cases, it will be faster. And then when it comes to expiring data, again, because segments are immutable, if you want to delete a document within an index, then it actually appends a list of deleted documents to that index. And documents are only really deleted when this merging happens. So if you have 2 segments and they're being merged and some of the documents are deleted, the new segment will only contain the documents that are actually kept. And so it's much cheaper to just delete an index. Like, okay, we have 7 of them. Tomorrow we create another one, so we just delete that index. It's basically deleting some files and updating the cluster state. While if you want to delete like 50 gigs or however you index in a day worth of data, that will be very expensive and cause a lot of merges. So this is why, I mean, in terms of performance, we've done quite a lot of performance tests with this kind of setup. And you can expect something like 10 times more capacity if you use this kind of design for logs and other time series data than if you just put everything in one index. And in terms of scaling, because you always create a new index, like every day, let's say today I create this index, right, with today's date. And I have lots of data, and then I need to add more nodes. And then I will know that, for example, tomorrow I can create a new index, but I can change the number of shards. I can make it have, because you cannot reshard an existing index, but if you're constantly creating indexes, then you can always decide the number of shards. And as I said, you can search in multiple indices. For example, you can use wildcards. You can have like a comma-separated list of indices and so on. Here I have no documents, but anyway, search kind of worked. And the thing that you'll probably want to do when you have these time-based indices is to have them inherit some settings that you would want to put up front. Like we put that new document earlier on with the mappings and the settings and so on. In this case, I can create a template that will match all documents, all indices having a certain name. And then here in the template, I would put the mappings that I've described earlier on with doc values and whatnot. And that's it. And you can also specify the number of shards. So now whenever I create a new index that will match this pattern, it will inherit all these settings. I wouldn't have to create indices manually to get those settings. And the second thing I wanted to say about like scaling, and this kind of relates to your question earlier on about having different like hardware specs for different kinds of data. Typically with logs, you only the hot data is the recent one. It's where you run most of your searches and aggregations, and then you have some sort of an archive. It's kind of a nice to have where people usually have more patience when they run searches and so on. So it makes sense to have like the hot data into some, let's say, beefy machines and the cold data on some maybe cheaper ones. And you can do that if you have time-based indices pretty easily. You would just go to the configuration, and in the configuration, you would flag nodes. For example, this one I put a tag on it that says hot. So this is a hot node, okay? The one that's already started. And I'm going to start a new one, and I'm going to tag it as cold. I mean, in production, you have multiple hot and multiple cold ones, but just for the sake of the demo. Okay, let me delete everything again so that we're not cheating. And I will put a template. There's no problem if it matches the same pattern as the template I just put. You can use order to figure out what's the order in which templates are applied, in case some settings are the same in multiple templates. And I would put in this template that I only want to allocate these new indices to the hot nodes. Okay, so I'm matching that tag hot. Okay, so now if I put an index, like today's index, and I look at the shards, meow, shards, cat shards. Okay, I can see that this new index is only allocated to the hot node, velocity 0, 1. It's not allocated to the velocity cold 0, 1 that I just started. So this means you can also over-provision in a smarter way, because if you divide your cluster this way, like hot and cold, you should obviously account for spikes, right? You can have like Black Friday, much more logs. But if all logs go only to these hot nodes, then I can have my buffer in only like a part of the cluster. And in addition to that, long-running searches will not affect my hot node performance that much. And also if I have like a spike in indexing, all my, let's say, long-term reports will not be affected by that because the cold nodes don't get hit. But anyway, let's say we're indexing in today and then tomorrow comes and that index is not hot anymore. So we would just change the settings, just like Rafael did earlier on with some other settings. And we would say we're excluding the hot tag and we're including the cold one instead. So now Elasticsearch will move, this is an empty index, so we'll move it in an instant. But anyway, Elasticsearch would move this index from the hot nodes to the cold nodes. So if you look at it now, it's both shards are on cold 0, 1. And I think that's pretty much all we had to say about Elasticsearch for today. So if you have any questions, and then we can move on to Logstash and Rsyslog and so on.
Okay.
Sure.
What's the impact of, say a node is offline and you have to move large indexes around the query speed, query time, something like that?
Well, it depends on your cluster, obviously. If you have 10 nodes and one goes down, not so much. If you have 3 and one goes down, it's more big of a deal. The thing I would look for is how many, because when a node goes down, when it takes all the shards with it, then Elasticsearch will have to recreate the replica, like promote primaries if you want. And that recreation of the replica means copy all the data from the primary shards to the replica. And you can control how many of these relocations, I think they're called. No, not relocation. Recoveries, yeah. How many concurrent recoveries happen? And typically, if you have like a large cluster and expect many nodes to go down, you would have that to a small number. And maybe if you want to do this manually, like a rolling restart, you would temporarily up that. Mm-hmm. But it's a dynamic setting, so you can change that. But yeah. Okay.
If you had in your logs some field which is either uninteresting or undesirable to search, say a blob,
Yes.
can you tell Elasticsearch not to put that in the indexes at all?
Yes, you can say index no. Like I had index not analyzed, you can say index no. And then you cannot search on it. You can still retrieve it through the source, but yeah.
Yeah. Yes?
Is there a mechanism to aggregate data by some time intervals? Say if you have a lot of hits and you just want to know within each given minute frame how many errors do we have and how many successes do we have instead of listing each one? Is there a feasible way to do that?
Yeah.
Yes, aggregations, right? The date histogram, time histogram ranges, and Elasticsearch provides appropriate aggregations to do that. You can just run a query and include an aggregation, and Elasticsearch will divide the amount of documents into buckets in an appropriate bucket that is defined by your time rate, for example.
Will it then only store the aggregate or store the full data set?
I'm not sure.
What do you mean by score?
Store?
Store, yes. What I was thinking is because one thing to do is you have a lot of data, it would be to just get enough servers that you can store all the data. Another option would be to segment the data by or aggregate them by minutes or something like that.
I know.
I think I see
Pre-aggregate the data before inserting into Elasticsearch, right? Actually, Elasticsearch don't do that out of the box. So you would have to pre-aggregate the data somewhere else and put the data already aggregated into Elasticsearch and include, for example, the range that is associated with that particular.
I think Logstash can do that. If we put stuff like in Kafka, I think
Yes.
Logstash can do that.
What you could do is you could have your main index, and then if you wanted to then do a roll-up, which is what you're talking about. If you're talking about doing a roll-up, then
Yeah.
you
Well,
could then query through Kibana or something,
Yeah.
pull out the data, and then push it into a different index. Which seems like would be a really efficient way to archive stuff over time.
Yeah, I just want to add something to this. So Elasticsearch isn't good at deep paging, because if you say, give me 100 results from result 1 million, then it has to retrieve 1,100,000 results, sort them, and give you the last 100. So that will probably blow up your memory. So if you want to go through a whole index and just aggregate stuff and put it in what would be a smaller index, then you have what is called a scroll, which is, like in relational databases, it takes like a snapshot of your index, and you just can go through it. You take page by page, and then you do your stuff and index it. And it's again something that you can do, for example, with Logstash.
Yeah.
Are the records themselves mutable, so that you can, for example,
Yes.
if you wanted to have a batch process that decorated them with classifications or something like that?
Yeah, but you can update documents. The trouble is updating actually means, because those segments are immutable, it means retrieving the document and indexing another one on top of it and deleting the old one. So that's pretty expensive compared to update. If you have big documents and you just want to update that tiny field, that's going to be super expensive. Yes. So you'll be better off in doing the enriching before doing the indexing. Yeah. Which is, again, something that Logstash or Rsyslog or something else can do.
And we'll show that. Okay, I don't see. Okay?
So it's probably a very basic question. I'm not sure I understand how. So let's say I have many apps with different logs.
Okay.
Does the info goes from the logs to Elasticsearch?
Does what? Sorry, I didn't get the last part.
So I have many apps.
Yes.
And each of them has its own log.
Yeah.
How do I go from the log files
to Elasticsearch? That is exactly
Perfect
what we're
question.
going to cover next.
Because
Yeah,
love
precisely.
that. Yeah, precisely.
So
because
go on, dude.
we are actually we're talking about Elasticsearch itself, and you are actually pretty bored by that point about Elasticsearch. So there are things that we need to talk about and show you about how to put those logs that you have actually to that Elasticsearch, because we are missing a whole piece of environment here. So let's get here. So we had the dog values, and let's introduce you to Logstash. So basically, Logstash is a piece of software that is built of three things: the inputs, filters, and outputs. The input is something that reads through the data. For example, we can have a file input that reads the local data from the local file system. We can have Kafka input that reads from Kafka, from Redis, from whatever we want. Then, usually those logs, depending on actually where Logstash is, you get the logs in some format, usually this is a raw format. And with filters, we can actually give the logs the structure or enrich them with some additional data if we already have the data, our logs in JSON, like from Rsyslog to something to Kafka, then we have JSON. If we just read through a file like here, we'll have a row, for example, Apache access log, which is a line of text. And then Logstash needs to get that particular log line, like we see here, the get/index HTML, use a filter, some kind of like a grok. I'll say a few words about grok in just a second. And that filter will give a structure to that line, changing it to JSON. We can specify the number of workers that will do that, which is basically number of threads we want to use. And then we have the output, which can send the data for further processing or for indexing. Here is an Elasticsearch, so Elasticsearch output. But we can also have a Kafka output, Redis output, so wherever we want the data to be stored. So now let's get back
Can you
here.
shut down the cold node, just in case?
This is a cold no?
Yeah. Kill it with fire. Thank you.
Yeah, killed. So let's now look at how actually Logstash configuration looks like to get the data from the local host and push it to a local Elasticsearch. First, I'll copy the configuration, and now we can look at it direct. Okay, so we have 3 sections. First, we have the input, which is the thing that I just highlighted. The input, which means that this is the part that reads the data. We specified that we want the file input, which means that it will read the local file. We provide this path, which is the path to the log file. We give a type, which we will use during filtering, and we specify the type, the start position, which is start from beginning Logstash. This is pretty simple. We take the file. Then we have the filter, which is actually the most interesting part of the configuration here. And now we have a conditional that if the type is equal to Apache, so the one that we just specified in the input, we will use a grok filter. A grok filter allows us to use grok expressions, which hides regular expressions in a way nicer let's call it, in a way now it's a dictionary. For example, here, the combined Apache log tells Logstash that the message will be in that certain format. That combined Apache log is actually a few regular expressions in that grok dictionary, but Logstash hides that from us and allows us to use one of the multiple entries defined in that dictionary. For example, the combined Apache log will be able to parse the Apache access logs and give them a structure and change them to JSON. Of course, you are not limited to using a single filter in Logstash. We could, for example, add the GeoIP filter, which would take the IP addresses and change them to a latitude and longitude. And we could then visualize that, for example, to look from where our clients get or things like that. And finally, we have the output, which is, again, a pretty simple thing. We have the output, which is Elasticsearch. We specify the hosts, which in our case is only a single Elasticsearch instance. And the local host, we specify the port. The manage template equals false tells Logstash not to manage the template because Radu already put the template into Elasticsearch, so we don't want Logstash to do anything with that. And we've commented out the workers, so we'll take the default value. Now, we can also tune Logstash just like we did with Elasticsearch. We just go to etc default Logstash, and we have a few properties like the number of workers minus W, and we provide that amount. We can also set the heap size for Logstash. Pretty simple, but sometimes useful, as it can be expensive memory-wise to process a lot of logs, especially if you have a lot of rules. So let's kill it. And now we can also, before we continue, we've used that virtual machine to actually test the data before we're showing you. So we need to remove the ScenesDB from Logstash. It's already removed. Yes. So the ScenesDB is the local database that Logstash uses to put information about where it stopped processing the files, all the inputs. Okay, so now let's delete the data so we are not cheating. Okay, we don't have anything, and let's start Logstash. And now, Logstash is already running.
It's running?
Yeah. Let me restart it.
Okay, good for it.
Good. Yes, of course. Ta-da! I should stop it and delete ScenesDB actually. Now. Let's
see if it works.
Let's see. Logstash is not that fast, so we will just look at where if the data is there. I'll just put a simple query here. The size 0 so we pretty print it. Okay, and let's.
So normally you
check.
would send JSONs to Elasticsearch unless your name is Rafal.
Yes, I'm a Solar user, so yeah.
Yeah, so there you go.
So there we go. We have data. It's being indexed. As you see, the total is constantly increasing. So we can now look at, let me show Kibana Discover, and we should see some data here. Okay, so we have data. So this is the simplest way to actually put the data, or one of the simplest way. You take the local stuff, you push it with Logstash and stuff like that. But Logstash is quite expensive when it comes to resources. So Radu will tell you something about another log shipper.
A lighter alternative, yeah. So you probably know about Rsyslog. Let me actually stop Logstash because I have a feeling that this went out of control here. That's the thing with live demos. They always crash something.
Always crash.
And I'm going to delete stuff just
in case.
just to be deleted. All right. So you're probably familiar with our Rsyslog. It's like the default Rsyslog daemon for many distributions. The thing about it, it's very light, very fast, and I think quite a few people know how capable it is. So I just want to share some of that because I'm pretty much an Rsyslog fanboy. There, I said it.
Pretty much.
So like Logstash is modular. You can have input modules, you can have message modifiers, and outputs. So the flow goes like this, what I'm going to show. You can tail files and obviously take a local syslog, and then that goes into what is called the main queue. You can have multiple stacks like this, which are called rule sets, but in this case, we're just going to use the default one. So things go to this main queue, and then on that queue, you have some threads which take batches of messages and then process them according to whatever you say them to do. In this case, I'm going to use normalize, which is a module that can, like Grok did, take unstructured data and parse it according to some rules and then make it JSON. And then finally, you have an Elasticsearch output module that lets you stuff things into Elasticsearch. So I'm just going to show you how that works.
Copy-paste.
Copy-pasting for the win. Right. Right, so this is going to be a bit longer, but bear with me, please. So first you're going to load the modules, okay? The first ones are for tailing local syslog. Like this is the local socket, this is for kernel logs, this is for tailing files, this is for parsing, and this is for shoving things to Elasticsearch. And then we start doing stuff. We tail this file, and then I'm going to define where our syslog will store its stuff. And then I'm going to define that main queue, which is pretty important. I'm going to say how many threads will work on the stuff, both for parsing and for sending things to Elasticsearch. And the size of my batches. And for queues, because you can have also action queues, but I'm just going to use the main queue here. For each queue, you can choose what kind of queue you want. You can get sorry, it can be in memory, it can be on disk, or it can be a hybrid, which is what I'm using here. It writes in memory until it reaches a watermark, and then it starts spilling to disk until it reaches a certain limit again. And then these workers will do the parsing, and this parsing will be done according to the rules specified here. So let me just show you how a rule will look like for parsing Apache logs. So you can have it in a verbose structure like this commented here, or you can have it something like this, which looks very similar with Grok rules, right? You have things like a word will go into a client IP field, a number will go into the bytes field, and so on. Let me go back to the config. Right, so after the parsing, I'm going to define the templates. And a template will basically build up a string. We'll tell our syslog to build up a string based on certain properties that it already parsed. So in the case of Apache logs, which are parsed by that rule, this is pretty simple because normalize already spits out a JSON in this variable called all.json. So our template, because we want to send JSON to Elasticsearch, will just include that very variable. For local syslog, things are going to be more complicated because you have tons of variables and you don't want to send them all to Elasticsearch typically. For example, you have the severity field, which can be a number or can be a text. You typically just send one of them. So in this case, I'm going to build a JSON based only on the properties that I want, like timestamp, host, the severity in the textual form, and so on. Then I have another template which will define my time-based indices, which to work nicely with Logstash, I'm going to use the default Logstash format. So basically, I'm just building an index name out of the timestamp of each log. And then finally, I'm going to push things to Elasticsearch. And here I have a conditional, like if the parsing with normalized worked, then I'm going to use that JSON template. And I'm going to send stuff to the Apache type. And if parsing failed, which means I have a system log, then I'm going to use the syslog template, which I defined earlier on, and I put documents in the system type. So let me start our syslog now. Wait, actually, I have to delete what would be a synsdb equivalent. Yeah. Which is a state file. Again, something where our syslog remembers where it left off. Again, it was already
strange.
Well, I did that actually before we left.
Okay.
You know, deleting a file twice doesn't hurt. Right. So this should go pretty fast. I should have the data here, hopefully. Yeah.
Yeah.
It's already here. And let me stop our syslog for now.
Yeah.
Okay. And the last thing we want to show, let me just start from scratch again. I'm going to delete stuff.
No.
I'm going to delete it. Kill it with fire. Okay. So the last thing I want to show is actually oh no, I forgot to say something about normalize and how it's different from Grok. Yeah, I totally forgot about it. Rafal said Grok uses regular expressions. Normalize can use regular expressions as well, but it doesn't by default. Because normally, when you would use normalize, you would use its specialized parsers. And when you do that, it will build what is called a parse tree. So for example, this one will parse system and syslog D and syslog NG. So basically, it's a nice way to... Sorry, you had a question? Or? No. Oh, okay. So basically, a nice way to scale out if you have multiple rules. It actually scales so well with multiple rules that I did some tests and I didn't see any difference in like parsing if you have one rule or if you have like 100 rules. It actually, performance depends on how long your log line is and not so much on how many rules you have. So it's very, very fast for this kind of normalizing. Obviously, you lose some of the flexibility that is given by regular expressions. But I think it's a pretty cool library behind it. It's called liblognorm, which, yeah, I wanted to share that.
Can you write your own parsers?
Yeah, of course, yeah.
And finally, you can, of course, choose Logstash to get the logs from local system and push them to Elasticsearch. You can do that with Rsyslog. But the real thing about all that stuff is that you actually can build up that pipeline. And imagine that you have multiple Ryslogs running somewhere, and they push the data to some buffer like the Kafka. So we read with file input, we use normalize, then we use Kafka with JSON template to push the data to Kafka, and we have already data stored there. But some functionalities of Logstash are not available in Rsyslog, like for example the GeoAP stuff, right? So we can't actually use Rsyslog for that. And to do that, we can just install Logstash and use that, and use a Kafka as an input to Logstash, not the local file system as we used earlier. So now we'll use the Kafka input plus JSON codec because this is the default. We already have the data in a JSON format that's done by Rsyslog, so we have less work to do on Kafka on Logstash side, and we can just read from Kafka and then output to Elasticsearch. You may ask why Kafka. This can also be Redis, for example, but Kafka is very, very nice, at least for our use cases. Mostly, it's very stable. It's not CPU bound, not memory bound. Yes.
Do you use Kafka's topics to separate that stuff out by functional domain, like system-based logs versus application-based?
Actually, no. We push data to a single topic. Just partition it in a way that we can have enough consumers.
Just for those people who haven't used Kafka, you can use topics kind of like queues.
Yeah. It's basically a publish, subscribe, right? Service, a queue that you can consume from. You can have multiple consumers. You can have topics that works. You can imagine them more or less like indices in Elasticsearch. You have partitions which are like divisions. You can have multiple consumers consuming from a single topic. So you scale out the consumers by actually dividing to multiple partitions. You can have again replication. It uses Zookeeper. It's very highly available. It can process hundreds of megabytes per second, both publishing and producing. Actually, the only thing that you're dependent on is your IOPS. Actually, so the limits is your machine, not the software itself. It's very, very, very nice when it comes to Kafka. And now we would like to show you in the last minutes how that works with all. So wait. Haha. I'll start up with running Kafka here and Zookeeper actually. So we'll go here. Where's that?
There.
Wait. And he already wants to show our Rsyslog, and he said he's small fanboy.
No, I said that.
Yes, small. Okay, so we start Zookeeper first. It's very fast. Okay, already started. We start Kafka. That again should be quite fast. Okay. We have a topic already created, but I'll show you how that's done. So we use one of the shell scripts provided with Kafka. We specify create. We tell which Zookeeper server we want to connect to because that's needed. We specify the replication factor and the number of partitions. For our demo and the tutorial, that this is one partition is more than enough, and we tell which topic we want to create, which is Rsyslog Logstash in that case. So we will copy those two configuration files, and I'll give voice to Radu again, so he can talk about Rsyslog.
Yeah, right. So that topic name, we'll have to use it in both configurations, obviously. So now the configuration looks quite similar to what you've seen before, except instead of sending to Elasticsearch, we will send to Kafka. And typically in this kind of a pipeline, you would want Rsyslog to be as light as possible because you would typically have lots and lots of servers pushing to a central queue and then Logstash doing the heavy stuff. So I would just limit it to one thread, having a small memory queue, and that's it. And then all the parsing and the templates would be the same. The output would be slightly different because it will push to Kafka. Again, using the same templates. This for parsed logs, this was for system logs, and you would just say where to connect and the topic name. So, yeah.
Thanks. When it comes to Logstash, it's again similar in a way, but we need an input that reads from Kafka because Logstash will read from there. So we specify the Kafka input, which Zookeeper to connect to, the topic identifier, which is the topic name, and again the type. We don't specify the filter here because in that, for the sake of the demo, we just will read the JSON from Kafka and we'll push it to Elasticsearch. But we could, for example, add new codec filters like GeoIP and then reach the data further. And of course, the output is the same Elasticsearch and without managed templates and stuff. So we can just start Logstash and start Rsyslog and go from there. See if that's all will work. hopefully. So again, let's go to Kibana. This will take a bit more time now, at least it should, because we have Logstash here running. Oh, okay. Really?
Is it really there, or did you not delete the stuff?
Let's reload the whole page and go to Discover.
Well, anyway, it should work. Trademark.
It should work. Wait. It should work. It should work. Please specify valid pattern.
Well, you already specified it. You just have to.
Okay.
Yeah, there you go.
There you go. We have the data. So I reloaded the page, so we have the data, and we did delete the data earlier. So we have 3 minutes, so I'll start to wrap it up.
Yep. Wrap it up.
So
Put it in a wrap.
one more thing. We gave the book for those who.
Yeah, if you didn't get a book
Radu,
like this, you can go. We have plenty remaining.
Yeah, this is related to actually performance monitoring essentials about what to monitor, what to tune about Elasticsearch. So if you want one, please get it. We also have a free book. We don't have it printed. It's available at Sematext about log management and analysis. This is the guy around the book. And if you're interested in the topics like this, we are hiring. Crazy people like we are working there. And that's all, folks, for today. And if you are, first of all, thank you for attending. Thank you for listening to us. Those are contact information for us. So if you would like to ask any questions and you didn't ask today or you won't ask now, do not hesitate to ask them, send a mail, ping us on Twitter or anything like that. And thank you for being here and have a nice conference.